In this video, we are going to discuss a very interesting topic, which is the DC power supply. Why is it very interesting? Because this is something that you see every day in your life. For example, the adapter, or what you call the adapter of your laptop. This is exactly what we call here technically the DC power supply. So what's the problem here? Why are you using, or why do you use the adapter every day to operate your laptop or your computer? This is because the electricity that you get from the electricity company, or the electricity that you get from the plug in the wall, it's usually AC voltage with RMS value in the range of 220 volt, or in some countries it's 110 or 120 volt RMS. So it's AC with RMS value of 220 or 110 in some other countries, okay? However, your laptop, your computer, it works with a DC voltage in the range of sometimes 9 volt or 12 volt. So how to convert this AC voltage that has a high RMS value, high amplitude, RMS in the range of 220 to a DC voltage to operate your computer in the range of 9 or 12 volt. This conversion happens through the adapter of your computer, or the DC voltage supply of your computer that you use, and usually it's a black rectangle that looks like this. You connect it to the wall here and to your computer or laptop here. So what happens? How can we convert from this AC voltage with high amplitude to a DC voltage with low amplitude? This is the topic that we are going to talk about today. Okay, so the first stage of doing that is a transformer. The transformer converts an AC voltage with high amplitude to another AC voltage in the secondary of the transformer, but with low amplitude. So the first stage is a transformer. Still, the transformer keeps the primary voltage at this side that comes from the electricity company. It keeps it in the secondary side as sinusoidal, but the purpose of the transformer is to reduce the amplitude. So it reduces the amplitude from 220 or 120 to a very small value in the range of 12 or 13 volt, but still it's sinusoidal. And then we use some circuit called a rectifier. This rectifier, it rectifies the sinusoidal voltage. And as we talked before about the rectifier makes all the signal or all the voltage in the positive side. It rectifies the voltage to be all in the positive side. So after the rectifier, it will convert the sinusoidal wave to all positive signal like this. And then in order to smooth down the fluctuations in the sinusoidal signal, we use a filter. And after the filter, it smoothes down the variations in the sinusoidal voltage, so it gives you something like this. Still, there are small variations, and in order to get rid of the small variations, what do we use? Something that we studied before. Exactly, we'll use the voltage regulator, the Zener diode voltage regulator. As we discussed before, the Zener diode voltage regulator is used to remove any fluctuations in the input voltage, and it gives you approximately constant voltage at the output, and then you connect this constant voltage to your load or your computer or any device that you wish. So we have these stages for the DC power supply. First stage is a transformer, and this transformer you will study in details in one of the power courses that you will study in the department here. But all what we need to know about the transformer is you have a primary voltage. This is a primary voltage, and this is a secondary voltage. The relation between them is related to the number of turns of the coil here and the coil here. So if the number of turns here is N1 and the number of turns here is N2, then the relation that we should know for this transformer is that Vp over Vs, the amplitude of this voltage, over the amplitude of this voltage equals N1 over N2. You can use here the amplitude, the maximum of the sinusoidal voltage here, and Vs is the maximum of the sinusoidal voltage at the secondary side, or you can use the RMS over the RMS. So this is either you use the peak Or if you want to use the RMS, you have to use the RMS for both. So you say V primary RMS over V secondary RMS. It will give you the same result. So either V primary peak over V secondary peak equals N1 over N2, or V primary RMS over V secondary RMS, it will give you also N1 over N2. So this is the only relation that we need to use for the transformer. Other details about the transformer you will study in more details in one of the power systems courses that you will study in the department here. The next stage, the diode rectifier and the filter, we are going to study them in our course. This is the focus of our lecture today. The diode rectifier and the filter, we'll study them together as one circuit. And then the voltage regulator, this is something that we already studied when we talked about the Zener diode and how to design the regulator using the Zener diode. Finally, this is your load. Also the filter here, you are going to study the filters in more details in the signals and systems course. In a different perspective, you are going to study the mathematics and how to design these filters. However, here we are going to study the filter from the circuit perspective as a circuit element, like using the capacitor to smooth down the signal without going into the mathematics of filters. Okay, so these are the different stages. It starts with, again, transformer, rectifier and filter. This is what we are going to talk about today. And then regulator, which is the Zener diode we already talked about before. Okay? So let's start with the first circuit. In the first circuit, and I prefer here to work on the board directly, so I'm going to just turn off the projector. So the first circuit that we are going to talk about is called the half-wave rectifier with resistive load. Half-wave rectifier with a resistive load. And simply here it looks like this. It's just a diode, and this is your load. This is R, which represents your load. This is the secondary voltage from the transformer. Secondary voltage from the transformer. And the rectifier basically is just a diode. You connect a diode in the middle between the secondary voltage that comes from the transformer and your load. So basically this is the first circuit that we are going to talk about. The output, of course, the output voltage is the voltage across the load. This is the output voltage here. Let's see how this circuit works. We'll consider first, in order to understand the circuit in an easy way, let's consider an ideal diode. Let's consider that this diode is ideal. And then we'll consider that it has a constant voltage drop or it has a piecewise linear model. But for simplicity, let's assume it's ideal diode. If this is an ideal diode and this is your input signal, with time, your input signal is a sinusoidal wave. It has a peak, let's say Vs peak. Vsp, this is the peak of your input signal, of your secondary voltage from the transformer. Okay? What happens here? How would the output look like? So if Vs, I think we discussed this before, if Vs is positive, in the positive half cycle, this cycle, the source is trying to push the current in the conventional direction of the diode. So the diode will allow the current to flow. And since it is an ideal diode, it will work as a short circuit. So the circuit basically will look like this. This is Vs, this is V output, this is your load. So this is the diode is on in the positive half cycle. The diode will be on, and V output, in this case, V output will be equal to V input. So in the positive half cycle, V output will be equal to V input. Again, the amplitude will be Vsp. Same amplitude exactly. However, in the negative half cycle, When Vs is negative, it tries to push the current in the other way. So the diode will not allow that. The diode will work, because it's an ideal diode so far, it will work as an open circuit. And if it works as an open circuit, then if it works as an open circuit, this is in the negative half cycle. If it works as an open circuit, then there is no current in this circuit, and V output will be 0. So during the negative half cycle, V output will be 0. Again, in the positive half cycle, V output will be equal to V input. In the negative half cycle, V output will be 0. And as you see here, we have rectified only, or we have passed only, the positive half cycle of the input. So the positive half cycle of the input passed to the output. The negative half cycle didn't pass. That's why we call this kind of rectifier, we call it half wave rectifier, because we are passing only half of the signal. Half wave rectifier. Why do we call it with resistive load? Because our load here so far, we have only a resistance. Later, we are going to see when we connect a capacitor along in parallel with the resistance, what will happen. But so far, this circuit rectifies only, or passes only half of the wave, the positive half of the wave. That's why we call it half wave rectifier. And it has only a resistance at the load. That's why we call it with resistive load. Okay, so here in the positive half cycle, V output will be equal to V input, exactly Vs. Okay, V output will be equal to Vs. This is S. Okay, and in the negative half cycle, V output will be equal to 0. Okay, right. This is if we assume an ideal diode. What happens if we assume that the diode has a constant voltage drop model? For example, the diode can be represented by a battery, VDO, and an ideal diode. So if we replace our diode with an ideal diode and battery, this is now our diode is replaced by this VDO. And this is our source, or our secondary voltage. Okay, this is our load. And here we replaced our diode with its model, with a constant voltage drop model, which is an ideal diode and battery. In this case, the diode or the ideal diode here will not operate if Vs is smaller than VDO. So it will start to operate only when the secondary voltage increases above VDO. So let's see if this is our Vs. If this is our Vs, it's a sinusoidal wave like this. Then, as long as Vs is below the value of VDO, which is usually in the range of 0.6 to 0.8, let's assume it's 0.7 for now. So as long as Vs is below the value of VDO, then the diode will be off, and the output voltage will be 0. So as long as, let's write it, Vs is less than VDO, then this will give you that this circuit will be off, diode will be off, and the output voltage will be 0, right? So here, let's try to plot it, plot the output voltage in blue. So the output voltage up to this point will be 0. Here, between this point and this point, again the output voltage will be 0. Again, from this point up to maybe here, it will be 0. And then when Vs is higher than VDO, when Vs is greater than or equal to VDO, what happens? When Vs is greater than or equal to VDO, this diode will start to be on. So it will work as a short circuit. So the diode will operate as a short circuit, this ideal diode, and the circuit will look like this. This is Vs, this is VDO, this is R. So the output here, the output voltage here will be Vs minus VDO, right? So the output here will be Vs minus the battery voltage, which is VDO. So always you will find that V output will appear as something like this, right? Smaller than Vs. So V output will be smaller than Vs. Smaller by how much? Smaller by the value of VDO. Again, it will be 0 here, and then it will appear here, but smaller than Vs. So this is how the output voltage is going to appear. Okay? It's smaller by VDO. What is so if the peak here is called Vs peak, then the peak here of the output voltage will be Vs peak minus VDO. Okay? So this is what happens if you assume a constant voltage drop model. So we assume here ideal diode, here we assume constant voltage drop model. You can also assume the piecewise linear model, and you calculate the output in this case, and we can do it quickly. If you assume that the piecewise linear model, all what you need to do is you will add another resistor here. So the circuit will look like this. So this is, let's write it. So this is the constant voltage drop model here. Let's assume piecewise linear. In the piecewise linear model, we can replace our diode with an ideal diode, battery, and resistor. RD, and the battery is VDO, and here this is our load, this is an ideal diode. All this is the model of our diode, right? And here we have our secondary voltage. Our secondary voltage basically it's a sinusoidal wave, Vs peak multiplied by sine or cosine sine omega t, right? And V output is here. So what happens here? What happens here is, again, the diode will be off, and always try to start by when would the diode be off? The diode will be off as long as the voltage here is lower than the voltage here. So as long as, I'm going to remove this, as long as Vs is lower than VDO, then the diode will be off, and if the diode is off, open circuit, this means that there is no current in this circuit, and V output will be 0. So again, it will happen something similar to what happened there in the constant voltage drop model, as long as Vs is smaller than VDO in this region, Vs is smaller than VDO in this region, Vs is smaller than VDO, the output will be 0. So the output will be 0 and the diode is off. So in this region, the output will be 0, here, here. And then, when Vs is greater than or equal to VDO, what happens? When Vs is greater than or equal to VDO, this ideal diode will operate and will be short circuit. And when it is a short circuit, let's replace it by short circuit, the output will be equal to what? Let's calculate the output. The output will be Vs minus VDO. This is the voltage across the two resistors here, right? And then we'll do voltage divider. We'll multiply by this resistor over the summation, right? So the output here, let's say diode is on, and the output will be Vs minus VDO. This is the total voltage across the resistors, multiplied by R over R plus RD. So this will be the output in this case. Of course, is smaller than the output in the constant voltage drop model. Why is it smaller? Because we have an additional resistor here. This additional resistor will take part of the voltage, right? Not all the voltage will go to the output, part of it will go to RD and part of it will go to R. So it will be divided, Vs minus VGO, it will be divided between R and RD according to the voltage divider rule. While there, the output was Vs minus VGO, right? So this is the difference between using constant voltage drop model and using the piecewise linear model. And here, again, if you want to plot or sketch V output, you will find that it will be very similar to this. However, the peak will be smaller, a little bit smaller. So the voltage itself will be a little bit smaller than in the previous case. Why smaller again? Because we are doing a voltage divider between R and RD, right? So the peak here, the peak of this voltage will be Vs peak multiplied by R, Vs peak minus VGO, Vs peak minus VGO multiplied by R over R plus RD. So this is here the peak of this voltage, while here the peak was Vs peak minus VGO on. Okay, so here we use the three models. We use the three models to solve the half-wave rectifier circuit with resistive load. Okay, here we have two important parameters that we care about when we design any rectifier circuit. We care about two things. We care about a parameter called the maximum forward current, and the peak inverse voltage. So we have two parameters that we care about. I need to remove something here. We have two parameters that we care about. Let's remove the curves for now. I just want to keep the circuits. Let's go back to the original circuit here. We had a diode, ideal diode, right? So we care about two things, two parameters that we care about. First parameter is called the maximum forward current, and the other parameter is called the peak inverse voltage. Let's start with the maximum forward current. What is the maximum forward current? Basically, the maximum forward current from its name, what is the maximum current that will pass in the forward direction of the diode? Why do we care to calculate this maximum forward current? Because when you design your circuit, you need to go and buy a diode that can withstand this forward current. You cannot go to the market and buy a diode that can take only 10 milliampere and you put it in a circuit where there is 100 milliampere that will pass. Of course it will burn, right? So you have to buy a diode that is suitable for this circuit. So in order to buy a diode that is suitable for this circuit, you need to know what is the maximum current that will pass through the diode. Okay? You cannot design your circuit for 100 ampere and you go and buy a diode that can withstand only 1 ampere. It will burn, of course, right? So you need to calculate what is the maximum forward current so that you use a diode that is suitable, that can withstand this maximum forward current. For example, if we use here the constant voltage drop model, you can calculate the maximum forward current in our circuit to be what? To be, in the constant voltage drop model, it will be Vs minus VGO over R. When we say maximum forward current, then you assume that the diode is on, right? You assume that the diode is on, otherwise there is no forward current. So when we talk about forward current, this means that the diode is on by default. So the maximum forward current here, if we use the constant voltage drop model, the maximum forward current will be I peak, let's say. It will be Vs minus VGO over R. But which Vs what's the maximum current that will pass? The maximum current will happen when the voltage here reaches its peak. When V secondary reaches the peaks. That's why we say I peak here, the maximum forward current will be Vs peak, the maximum value of Vs minus VDO over the resistance here, right? This is the maximum current that will pass through this circuit. If we want to calculate the maximum forward current here in this circuit, then it will be the maximum forward current. It will happen when again the source reaches its peak. When the source reaches its peak, the value of it will be Vs peak minus VDO over the summation of the resistors. Vs peak minus VDO over the summation of R plus RD. Someone may ask me, what about the diode? We assumed it's on, and the ideal diode, when it is on, it will be a short circuit. So the current that will pass through this circuit, it will be Vs minus VDO over the two resistors, divided by the two resistors. And we want the maximum current, so the maximum current will be Vs maximum, which is the peak of Vs peak minus VDO over the summation of these two resistors. So here we calculated the maximum forward current in case you use the constant voltage drop model or use the piecewise linear model. Okay, if you use the ideal diode, of course, in case of ideal diode model, then the maximum forward current will be Vs peak over R. Okay, and then once you calculate the maximum forward current, you have to buy a diode or use a diode that can withstand this maximum forward current so that it doesn't burn later when you use it. So this is the first parameter that we care about. What about the second parameter? And this is a very important parameter. We need to calculate it for each rectifier that we are going to describe or use. The second parameter is called the peak inverse voltage. And the peak inverse voltage second parameter is called peak inverse voltage. And we have abbreviated as PIV, peak inverse voltage, PIV. What's the peak inverse voltage? From its name, peak means the maximum. Inverse voltage means the voltage in the inverse, in the reverse side of the diode, the reverse voltage of the diode. So what is the maximum reverse voltage that will affect the diode? Again, peak inverse voltage. Peak means the maximum. Inverse voltage means it's a reverse voltage on the diode, right? So we need to calculate what is the maximum reverse voltage on the diode. Why is that again? Because we want, in order for our rectifier to work properly, we don't want the diode to break down. We want the diode to operate without breaking down. Like, in order to avoid breaking down the diode, we need to calculate what is the maximum inverse voltage that will affect the diode, and then we choose a diode with a breakdown voltage that is higher than the peak inverse voltage. Be careful, Shabab. So here, when we talk about the maximum inverse voltage, if this is our diode, usually this is the current of the diode, and this is the voltage of the diode. Right? These are the conventional directions of the current of the diode and voltage of the diode. When we talk about the inverse voltage, it's the reverse voltage of the diode. The reverse voltage of the diode is defined, it's the voltage of the diode in the reverse direction. So it will be defined as negative here and positive here. Let's call it Vx, for example. So this is the reverse voltage. So the reverse voltage is negative Vd. So when you put an inverse voltage on the diode, when you put a voltage of the diode to be negative 5, the inverse voltage or the reverse voltage of the diode will be 5. So if the voltage of the diode is negative 5, you put the reverse voltage of the diode of negative 5, then the reverse voltage will be 5. We say that we have a reverse voltage of 5. So you can say that the voltage of the diode is negative 5, or the reverse voltage on the diode is 5. So here, when you calculate the peak inverse voltage, the maximum inverse voltage that will affect your diode, and you find it to be 5, can you buy a diode that breaks down at 3, for example? No, because it will break down, right? So you need to buy a diode that breaks down at, for example, 9, or it breaks down at 10, so that it doesn't break down in your circuit. In the operation of your circuit, we calculated the maximum inverse voltage that will affect, that can affect, or it can happen that will affect your diode, the maximum inverse voltage to be 5. So you have to buy a diode that doesn't break down up to 5. It has to break down later, like at 7 or 9 or 10, right? Usually they choose the breakdown of the diode to be 50% higher than the peak inverse voltage. This is why this parameter is important. We calculate the peak inverse voltage and then we buy a diode from the market that has a breakdown that is 50% higher than this peak inverse voltage. So for example, if you find that the peak inverse voltage that will affect your diode is 5, then you have to buy a diode that has a breakdown at 7 or 9 reverse voltage. 7 or 9 reverse voltage means -7 or -9 diode voltage, right? As I explained here, the reverse voltage is negative of the diode voltage. Right. How to calculate this? You have to look at the circuit. And since we are talking about the reverse voltage, the diode will be off. You ask yourself, what is the maximum value of the reverse voltage? What is the maximum value of this Vx? So for example here, let's go back to our circuit. Our circuit originally was a diode, only a diode here. This is our diode. Where is the input voltage? Where is the diode voltage? The diode voltage is negative here, positive here. Where is the reverse voltage? The reverse voltage is Vx. Let's write an equation for the reverse voltage. An equation for the reverse voltage would be, according to Kirchhoff voltage law, Vx plus Vs equals V out, and then from KVL, and then Vx equals V out minus Vs. V out minus Vs. Now we are talking about a reverse voltage, so we are talking about diode will be off. You have to assume that the diode is off because we are talking about a reverse and inverse voltage. So if the diode is off, V out will be 0. If the diode is off, V out will be 0. So Vx will be equal to minus Vs. Now the question is, what is the peak of this inverse voltage? This is the inverse voltage from the circuit. What's the peak of this inverse voltage? The peak of this inverse voltage, the maximum of this inverse voltage, it happens when Vs reaches its minimum, right? Because this is negative Vs. The maximum of Vx happens when Vs reaches the minimum value. So it will be negative Vs minimum. What is the minimum of Vs? Vs is a sinusoidal wave. Vs is a sinusoidal wave. It goes from Vs peak to minus Vs peak. What's the minimum of Vs? The minimum of Vs is minus or negative Vs peak. So it will be negative, and the minimum of Vs is negative Vs peak. Then the peak inverse voltage will be Vs peak here. So the peak inverse voltage in our circuit, will be Vs peak. And this is how to calculate it. First, put the inverse voltage on your circuit. This is the inverse voltage of the diode. Assume that the diode is off. Write an equation for Vx in terms of V input and V output. We know that since the diode is off, V output will be 0. So Vx will be negative Vs. Ask yourself, what is the peak value of Vx? The peak value of Vs, the maximum, happens when this is the maximum. And this is the maximum when Vs is the minimum, because this is a negative sign. And Vs is minimum, its value is negative Vsp. So minus Vsp, it will give you V secondary peak, the peak of the secondary voltage. And this is the peak inverse voltage of our diode, then you have to go and buy a diode that doesn't break down before Vs peak. That doesn't break down before Vs. It has to break down at least 50% higher than this Vs peak. We'll stop here in this video and we'll continue in the next video, inshallah.